All right, today's notes are on redox reactions and spontaneity. So we got Gibbs free energy is the thermodynamic function used to predict if a reaction will occur spontaneously or not spontaneously. So, anybody remember when delta G is negative or positive, there's excess free energy. So close. Negative. Let's go try. When delta G is negative, there is excess free energy, and the reaction is, anybody remember? Spontaneous. And then we got the opposite. So when the delta G is positive, the reaction is non-spontaneous. Oh my gosh. Spontaneous. There it is. All right. So and you can calculate this from the cell potential. And we got the equation is delta G. This was in the Pearson. It's also in the Zumdahl. Anyone? Negative N times F times E cell. That's the equation. And that equation is also in your packet. It's on the first page, the equation page, so you don't have to memorize it. All right, Faraday's constant. This is also in your data booklet. 96,500 over mole. Just double checking what page is it on. So here it is, 19.1. This is on page 1 of your data booklet. And then Faraday's constant, I believe, is on the next page. Faraday's constant, there it is. Oh, you can't really see that. It's tiny. Sorry about that. 9.65 times 10 to the 4th Celsius moles to negative 1. That's on page 2 of the data booklet. All right. So then we got N. N always in chemistry stands for moles. Number of moles of electrons. Oh, there it is. Okay. Thanks. Transferred in the reaction. And then E naught is cell potential. Difference in the half reactions. All right, so a spontaneous reaction is one that has a negative value for delta G or a positive value of E cell. So you might want to highlight, underline that. Kind of sums it up. And we got HCl dissolves silver metal and forms Ag solution. Write a half reactions, or both half reactions, and calculates H2 gas. Okay. So that's just my overall reaction I'm writing, just so I don't have to visualize it in my head. All right. So the aqueous oxidation states: hydrogen's +1, chlorine's -1, chlorine's -1 here, silver's +1. And if we got a solid metal, it's 0. If we got a diatomic element, it's 0. So now we can decide what is oxidized and what is reduced. Hydrogen is going from +1 to 0, so that is reduced. You got it. So it's gaining electrons.
Does it matter if the equation's balanced?
Is it? Oh, it's not balanced right now. It will. It'll impact it when we balance the electrons for the half reaction. So yes, it does matter. But you don't even have to write this. That's just so I don't have to visualize it in my brain. All right, so we got hydrogen aqueous reacts to form H2 gas, and we're going to 0. And when we reduce something, where did the electrons go? Which side? All right, so we're gaining electrons, so we put it on the left side. So this is reduction. Then we'll do the oxidation, which is silver. Solid is forming, in chlorine I don't have to write because it's spectating, so I'm not going to write that. So we're losing an electron, so we got to show it on the product side, electron. We got one electron, one electron. All right, and really to find the cell potential, we don't really need to balance it because the coefficients aren't going to impact those values. But technically, in order to get 2, I would need 2 of these H pluses to be reduced to form that. But that's not going to impact our overall answer because we're looking at the electrode cell difference, which is, anybody remember? You basically take the oxidation half plus the reduction half. You got it. So that was from yesterday. Reduction plus oxidation. You got it. Had that reversed. So reduction plus oxidation. All right. So we're dealing with reduction, which is the hydrogen. And that is right here. H plus plus 1E. Looks like it's 0. Even though we got 2 of them going on, doesn't matter. Still, well, if it was 1, you wouldn't multiply it by 2. 0, you're not going to multiply it by anything. So we got 0. All right. And then the oxidation is silver. Oh, there it is right there. But this is being reduced, but we want to show the oxidation version. There it is. Okay, read the directions and you know what's going on. In my head I was thinking, oh shoot, I wrote an example, that's wrong. Okay, so will it happen? No. So therefore this is probably a non-spontaneous reaction. So it's non-spontaneous. Could you put it into an electrolytic cell, put a current into it and make it occur? Yes. But for a voltaic cell, this will not work. Nothing will happen. And you're going to see that tomorrow in the lab. Some of the things are going to be quite uneventful because they're non-spontaneous. All right. So moving on to the next one, we got bromine can oxidize iodine to, not iodine, but the iodine ion to I2. But however, Br2 cannot do the same with chlorine. All right. Well, let's prove this. Let's show it. So I'm going to put Br2, and I'm just going to say Ki. K is going to be my spectator ion. Unless you just want to show I minus, you could do that too. -1 plus 1. This is 0. And we got I2 is 0 plus KBr. 1 minus 1 plus. Okay. Potassium spectating, we don't deal with that. We're going from 0 to -1. That is being reduced. You got it. So Br2 is going into Br -1 aqueous. And let's see, 0. Reduction. So it's reduction, our electrons are being added. So we got electron. Technically there's 2 of them. So in order to get 2 of them, how many electrons need to be added? 2 electrons. All right. So just so we don't forget what that is, that's reduction. And then we've got iodine going into I2, 0. This is being oxidized because we're gaining, no, we're not gaining electron, we're becoming more positive in charge, so we're losing electron. So therefore electrons on this side. But in order to do that, we're going to need 2 of these, and 2 electrons would be released in that process. Right, and that's oxidation. So then we got to look at the electrode potential, the E cell. And we're looking at bromine to Br minus is, there it is. And looking at it, it is the reduction 1.09. And then we've got the oxidation part is iodine, which is right here, and that's 0.54. But again, this is showing it being reduced. We want to show it oxidized, so we flip the charge to negative 0.54. And that will equal our E cell, which is 0.55 when you plug in your calculator. Volts is the unit. And it looks like that works, and that's what it says. It can oxidize iodine. All right, so now let's find some space and try to do the other one where bromine is doing it to chlorine. So I'm going to have Br2, let's just write it out. We'll say KCl. Cl2 plus KBr. So that's my equation. So let's do the first one. Br2 turns into Br minus, and that's aqueous. There's 2 of them. Going to 0 to minus, that's reduction. And so electrons are being added. And if I got 2 of them, I have 2 electrons. Questions so far? Okay. Next one, we've got chlorine. Say we got Cl minus, aqueous, form Cl2, 0 charge. And this is oxidation because we're going negative to a higher number, so we're losing electrons. And so we're losing electrons. Electrons go on the product side. And we've got 2 chlorine, so 2 chlorine, so 2 electrons are being given off. But again, balancing it isn't going to impact our E cell. Okay, so bromine, well, I know bromine's like 1.09, right? That's the reduction. I found that already. Plus the oxidation for chlorine. Where's chlorine? There it is. So 1.36, but this is the reduction format. We want to show oxidation, so we flip the sign to negative 1.36. And that's going to give us an overall negative number. Doing the math quick. 36 minus 9 is 27. Thank you. That's going to be negative 20.27, which is not possible because E cell has to be positive. So this is proof supporting our idea that Br2 cannot oxidize chlorine. So, there we go. All right, we got one more. Here's an example of delta G and spontaneity. So it says, is this reaction spontaneous? So you're going to have to do the delta G problem. And going up here, if delta G is negative, it is spontaneous. So if it's not, then it's non-spontaneous. Oh, remember that equation up here? We got Faraday's constant, that's fine. Moles is the coefficient in front of the number of electrons. E cell, we got to find E cell, so we got to do those half equations. It's like a little pyramid that we're building. And in order to get to the top, delta G, we got to do all the bottom stuff. All right. Nice, our equation is written. That's helpful for me. We got copper 2 plus going to copper 0, iron 0 going to iron 2 plus. So copper is being reduced. So reduction is going to be Cu2 plus aqueous, and then we go copper solid 0. And reduction means we're gaining electrons, and it looks like we're gaining 2 electrons. So I'm going to put a 2 coefficient, and number of moles of electrons transferred in the reaction. So that 2 coefficient is going to be important. What was that? Let's just get the cell potential of copper. So we got copper. I don't see it. Here it is. And we're the one that's losing 2 electrons. There's 2 types of coppers. This one's losing 1. This one's losing 2. So it looks like 0.34 is our reduction. All right. And then oxidation is iron, solid, 0 charge, Fe2 plus aqueous. It's oxidizing, so we're losing electrons, and there are 2 of them that are being lost. All right, so looking at oxidation, iron being lost, here we go. It looks like it's negative 0.45, but this is shown in the reduction, so we got to put positive 0.45. Reduction plus oxidation, the E cells, is our overall E cell. I'll just do 0.34 plus 0.45 equals 9.7. Is that what you guys got? 0.79? Did I add it right? Okay. But that's not the final answer. That's just our E cell. We want to find the delta G to see if it's spontaneous or not. And our delta G must be negative or positive to be spontaneous? Negative. All right. So we're looking for a negative number. We got to type in negative N, and it looks like 2 is our moles of electrons. So negative 2. Faraday's constant, 96,500. And then we times it by our E cell, which is 0.79. Oh, sorry, you didn't see that. There it is. So negative 2 is our moles of electrons. There's 2 of them. 96,500 is Faraday's constant. 0.79 is E cell. And I'm getting negative 2 in front. So that's our moles, negative N. So that gives us there it is, negative 152,470. Key to our answer is negative. So is it spontaneous?
Yes.
Yes, it's spontaneous. We kind of already knew it was spontaneous. Why? The E cell was positive. If E cell is positive, it's spontaneous. If E cell is negative, it's non-spontaneous. Yeah.
And what's the point in finding G if you know if the E cell is positive, you know it's going to be spontaneous?
Because that's what the question was asking. So could you, could you answer it without finding delta G? Yes, you could answer the question. But you wouldn't be able to answer the calculate delta G for the reaction. So, yeah, and so delta G relates to thermodynamic energy. So it's just showing that redox, delta G comes back. It can be used for redox reactions also. Yeah.
A problem like this where you're dealing with like 2 metals here, could we just look at like the metal, like what is it, the reactivity chart?
That's an even quicker way, yeah.
Okay.
You could. Yeah, so there's a lot of different ways.